Okay, I'm going to clean up that last example explanation where we had f of x equals square root of x on 0 to 5. Of course, we came up with the inverse function as x squared. So if we write it like we normally like to write the inverse function instead of f inverse of y as y squared, we're just going to use x's and say, hey, f inverse of x is x squared. Well, if we have that, what's the derivative f inverse prime at x? If I take the derivative of x squared with respect to x, I get 2x, right? So we have that over here. Then let's go back over here. If I take, that's x to the 1/2 power. If I take f prime at x, the derivative of x to the 1/2 is 1/2 x to the minus 1/2, or 1 over 2 root x. So we have this for our function f. And then, of course, we said, hey, let c equal 3. And so we said, what's f of 3? Well, plugging in into the f function, that's square root of 3, right? So d equals the square root of 3. So we had that as well. So let's just go back to the theorem and see what the theorem said. So the theorem said, first of all, f was continuous and monotonic. It is. If the derivative exists of the inverse exists at d, so if the derivative exists, so f inverse prime, let's just write the f inverse. I'm drawing the prime there. If f inverse prime at d is going to equal 1 over f prime at c, if f prime at c exists and is not equal to 0, which let's do that. So what color is that? Let's just work on this side. That's going to be the blue, right? Because that's f prime. So the right side is 1 over f prime at c. So I'm going to write in what is c? C is 3, right? So this is 1 over f prime evaluated at 3. Well, what's f prime at x? F prime at x is 1 over 2 root x. So the right side is 1 over, once again, we had that 1 over to start with, but f prime at 3 is this whole thing. So that's 1 over 2 root 3. So it's 1 over 2 root 3, which is 2 root 3. So that would be the right side of this equation is 2 root 3. And I wasn't really showing that for you, I don't think, very clearly at the end of the last video. And then let's do the other side. So this is f inverse prime at d. Well, what's that? That's f inverse prime evaluated at d. D is the square root of 3, right? But what's f inverse prime of anything is 2 times that anything. So what's this equal? This equals 2 times that anything is the square root of 3. So the left side of the equation is 2 root 3, and the right side of the equation is 2 root 3. And these things are equal. So everything works out swimmingly well. And the best thing about it, as I was hoping, is when we have specific values given here, then we don't have to worry about writing that as f inverse of y equals y squared. We can just go back to the normal notation. So this is what I was trying to do early on in that example where I did it in general and got messed up because I was using this notation, but their dx dy was denoted as f inverse prime of y. And of course, y is the output. D is the output here. C is the input. But we're all good when we can plug in specific numbers. Makes life a lot easier. Then it doesn't matter if this is called an X or a Y because we have some particular thing that we're plugging in. So hopefully that helps, clears it all up, and should be able to finish out 5-1 on what I'm asking you to do for the evens. And then we'll get going on the natural logarithmic function, which we did a little bit of stuff with the natural log, not much. So we'll dive into that a little bit deeper next time. Thanks.